This technique is frequently known as reduction to linear form, so therefore we know from our GCSE days that if we've got anything of the form y equals mx plus c, that as long as our axes are x and y, then our straight line will have an intercept, and depending on the steepness, it'll have a gradient. And this particular technique was very, very, very useful when old people like me were in school and we were doing things like physics and chemistry and we're collecting experimental data, and you end up with a curve. Now it's really quite hard to fit a curve properly, whereas if you can actually use logs, and we actually had access to log graph paper, so we had log and log number paper and log paper, which is guaranteed to do your eyes in. If you actually try looking on the internet for a piece of log graph paper, it will the gridding will really hurt your brain. But the idea is that, relatively simply, that if we log certain things, we can actually get them to behave themselves. So in our particular case, reading the question, we're looking to graph log to the base 10 of q against log to the base 10 of p. So we're looking to produce a log 10q against a log 10p. And what we want to know is the gradient and intercept of this. Now, for someone like me, this is a really simple piece of work. But then I've been doing it for a lot of years. But the clues are all there. This question has got all the clues for you. You've got to remember your log laws. It's important that you remember your log laws. And in fact, these laws work in any base. So I'm just going to write log. Later on, you will experience log to the base e, but most of the time people work in log base 10 because that's our natural number system. You can actually work in any log base, but it will work any way you want. So we've got that log of AB is the log of A plus the log of B, because logs are powers. And if you want to multiply two things together, you simply add the powers. You notice I've said it's a double implication because log of A plus the log of B will give you the log of AB. Log of A divided by B is the log of A minus the log of B, because if you want to actually divide, you subtract powers. And the other one we commonly use is that log of A to the n is n log A, because what it is log of A times log of A times log of A, which is repeated addition of log A n times, hence it's n times the log of A. And those are, you would normally expect in a question like this to use at least two of those three techniques. So our function is q is equal to 1.25 p3. So we've got q is equal to 1.25 p cubed, p3. And when we log, and no doubt at some stage during the course of writing this I will forget to put my 10 in there, but you can actually correct me. You can only log single terms on each side. You can't log across an addition, you have to bracket the whole lot. But we don't have one in this particular case, so we don't have to worry. We can just go, right, this is 1.25 p cubed. Now, what I'm looking to do, remember, is to end up with a log p against a log q. So therefore, all I need to do is unpack this side here, because I've got my log to the base 10 of q. Right, I can see that I have got a multiplication by 1.25 and then a raise to the power 3. So therefore, I'm going to use, this is log to the base 10 of 1.25 plus log to the base 10 of p cubed, because there is an operational multiplication between the 1.25 and the p cubed, and therefore I have now got log to the base 10 1.25 plus 3 log to the base 10 of p, and I don't need the bracket in on the p or indeed the 1.25 or in fact the q. It doesn't make any difference. Now, so log to the 10 of q is equal to 3 log to the 10 of p. You must be consistent with your base plus log to the base 10 of 1.25. And if I compare that to my linear form, y equals mx plus c, I can see straight off that m's got to be equal to 3 and c is going to have to be log to the base 10 of 1.25, which you can evaluate on a calculator if you want, but log to the base 10 of 1.25 is the most accurate answer. Why do more work than you need to?
The answer to the question mentions the use of log scales and why we might want them, and refers to science. Physics in particular is a subject where we often use log graphs. We might use them in biology for any sort of exponential growth type situations. And you can have a look at that if you haven't studied any of those subjects. If you want to have a look and see why it's a useful thing, you could have a look on the internet. I've decided to show you an example that's very pertinent today, which is carbon emissions or CO2 emissions. So what I did was get the figures, which are in these two columns. We have the year and then the million tons of CO2 emissions, and they go back to 1751. These early figures may not be that reliable, but they certainly will become reliable as we get into a more scientific age, and they're pretty reliable when we come up to date. With these columns we can then create points. So what we would type in is just that into the cell, and then we can drag it down like you do on an ordinary spreadsheet, and that's then formed all the points. So these are the points on here. Column D is the log base 2. If I click on one of them, you can see it's the log base 2 of the emission figure. And then the column E makes points out of them, and that's what you can see on this graphics 2 window. Very useful feature of Geogebra is to have two different graphics windows. There's also the 3D window, which you may have seen. Anyway, going back to the log graph point, this is a graph where clearly the bottom isn't a log scale, it's actually a linear scale in years for both of them. But this one goes up in actual tons of emissions, and this one is a log scale. So that means that if we take, say, 10, 2 to the power 10 is about 1,000, so that's just after 1880 would be about 1,000, and that's right down here on this one. Obviously, if that's 10,000, then down here we have 1,000. Now, you can probably see at least one advantage of this graph straight away. When we look at these figures, because they get so large when we get to around now, the whole graph is crushed down. So these 100 years here look pretty much stable. But actually, if we look on the log graph, we can see that they are going up steadily. You may want to think about why 1751, why start there? Think about history, have a look at industrial history. But what we see is that we've got a steady rise there. There's some hiccups around this time, so you might think about your GCSE history if you did it, and why that might be, and sort of hiccup around here. I say hiccup, it's actually a good thing because it steadied off, but then it started to rise again. From about 1980 you can see a slight change in the gradient, and that's around the time when the mainstream was starting to understand the problems with the environment. Anyway, just a little snippet to show you how useful a log scale can be in illustrating data.